Welcome to video 2. So in video 2 we're gonna do pages 3 and, that's right, page 4. So this first question we're looking at here, number 17, is about energy of reactions, or enthalpy, heat of reaction. Enthalpy, heat of reaction. So in these reactions, we have reactants on one side, and we have products on the other side, and they are of course separated by the yield sign or arrow or whatever. But as we look at them, we see in A that these reactants are coming together to make carbon dioxide, they're making water, and they're making energy. Well, in B, we have a reactant coming together with energy, and making products. In C, we have reactants coming together, making a single product, and they're making energy. D, we have reactants coming together with some energy, making products. So in A and C, energy is being made. And it's being made, therefore it is negative, the value is negative, it's exothermic, it's releasing energy. In B and D, we are using the energy to make products. That energy is being added to the reactants, and it's taking energy in to make these products. Number 18, define the molar heat of fusion of a substance. Molar heat of fusion is often also called molar heat of melting, but not very regularly. Those two terms mean exactly the opposite of each other. The opposite of melting is freezing, and the opposite of freezing is melting. If you thought the opposite of melting was boiling, you're wrong. We'll get more to that in a little bit. The opposite of boiling is condensation, by the way. So molar heat of fusion, or melting, is the amount of energy to melt or freeze 1 mole of whatever the substance is. So you have taken that substance and you've cooled it down a whole lot, and you've reached its freezing point, and now you have to take out just a little bit more energy to actually make it freeze. Or if you're melting it, you've put some energy in, the temperature's been increasing, you've hit the temperature at which it's going to melt, but it doesn't melt until you have all of the energy in there, so there's a little bit more energy called the molar heat of fusion, or melting, that's required to melt it. Now, I keep using these two terms interchangeably when in reality people only really ever say heat of fusion. And how would they indicate melting versus fusion? With a sign change. If you are melting things, it's positive. You're putting heat in to melt it, so you have a positive heat value. If you're freezing things, it's negative. You're taking the heat out. Number 19. How much energy would it take to melt 36 grams of ice given the molar heat of fusion is 6? So these units here are kilojoules per mole. Kilojoules per mole mean that these grams have to be converted to moles first. So how do you convert grams? Ye old periodic table, or even a modern periodic table if you'd prefer, instead of the ye old one. So you take the 36 grams and you convert it into moles, and you have moles of water. And then there's an equation we give in the notes that enthalpy times moles equals heat. You can also just do this from a units perspective. You could say, well, I've got 6 kilojoules per mole. This is 2 moles. 6 kilojoules times 2 moles divided by 1 mole. These moles cancel. You get 6 times 2 equals 12 kilojoules of energy going in to melt the ice. And then number 20. Define the molar heat of vaporization for a substance. Molar heat of vaporization, similar to molar heat of fusion, is the amount of energy required to vaporize a mole of substance. What is the opposite of vaporization? I can hear you thinking. It is condensation. So you could also say molar heat of condensation. It is the exact same amount of energy, just with the opposite sign value. So vaporization is positive. You have to put energy in to vaporize it. Condensation is negative. You have to take energy out of the particles. So when water particles, here you go, here's your glass. Whoop, boop, doop, doop. Got a nice glass of cold ice water. Look at these ice cubes here. Right. And there are gas particles floating around the room. Boop, 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 and they hit the beaker and condense. That's because some of the energy has been taken out of the gas particles. They've slowed down. They've condensed on the side of the glass as their energy has been removed. If you remove 1 mole of water from the air, 1 mole of water removed from the air would have the equivalent energy of molar heat of vaporization, but it would be a negative sign instead of positive. 21. What is happening to the average kinetic energy of the molecules during section 1? Let's explain this graph. Here we have some solid substance, some liquid substance, and some gaseous or vapor style substance. And then on these two plateaus, they are changing phases. So you go solid, solid liquid, liquid, liquid gas, gas. So we could say the solid, now it's melting, now the water's getting hotter, now it's boiling, now the gas is getting hotter. So what's happening in step 1? The kinetic energy is increasing, the temperature is increasing, there you go. What is the name of process happening on 4? Vaporization or boiling. What would be the name for the process happening during section 4 if it were going the other way? What do you mean going the other way? We mean literally, if this graph was doing this, the steam is cooling off, then it condenses for a while, then the liquid gets cooled off, then the liquid freezes, and then the ice gets colder and colder and colder and colder and colder. Of course, it can't get any colder than absolute zero. But, you know, let's say that we're doing the reverse processes in order. So 4 would be condensation if it was going in reverse. Melting point is 0 for this substance. You can tell because that's where it flatlines. Boiling point is 100. Are all heating and cooling curves the same? No. I'm going to draw the heating and cooling curve for a substance called tert butyl alcohol. That's tert butyl alcohol. So tert butyl alcohol is a solid. It hits a little bit above room temperature, and then it melts. And then you warm it up just a smidge, and then it vaporizes, and then it's all gas. And it melts at something like 27 degrees Celsius, and it boils at something around like 72 degrees Celsius. So that's a different heating and cooling curve for a different substance. But you can tell by the plateaus and where they correspond to the temperatures what is occurring there, what temperature it's occurring at. So we have solid, melting, liquid, boiling, and then all steam. This is, again, for tert butyl alcohol. I think I have those two values approximately correct. When given a quantity of water heated at a constant temperature, the phase changes, blah, blah, blah. Why does it take longer to go from liquid to gas than from liquid to solid or solid to liquid? Now this says, and this is true, the heat of vaporization is greater than it is for fusion. But the more important question here is, why does it take more energy? Water molecules are bounded or bonded to each other very weakly between a hydrogen and its oxygen. The electron pair here and that hydrogen kind of get attracted to each other through what is called a hydrogen bond. And if you're going to vaporize something, you have to take this molecule here and completely separate from this molecule and all others. So every hydrogen bond in the water has to be broken. Whereas when you melt something, you only have to move some of the hydrogen bonds, a much smaller quantity for the water molecules to be mobile. So the big difference between melting and vaporization is the quantity of hydrogen or intermolecular bonds being broken. Where are we? Other than on spring break. Number 27. Oh, we just flipped the page. Determine what it takes. That it takes 18 kilojoules of energy to vaporize 3 moles of chemical X. What is the molar heat? So we know the amount of energy, we know the amount of moles. 18 divided by 3 means 6 kilojoules per mole. In number 28, these three forces are between molecules. Let's just remind everyone that molecules are made from non-metals. Non-metals, hiding on the right side of the periodic table, since Mendeleev built it. So when you have a bunch of non-metals connected together through covalent bonds, they may be very well balanced molecules or completely off-balance molecules, just depending on how you draw the Lewis dot structure and how they're put together. If they're very off balance, they are funny to observe, meaning that they'll have hydrogen bonding only when you have hydrogen in one of these three elements bound to hydrogen. This is an extremely off-balance molecule when it has fluorine, oxygen, or nitrogen attached to hydrogen, and this extreme off-balance leads to very strong intermolecular forces. So the molecules are attracted to each other very strongly. If they're just slightly off balance, we may have dipole-dipole interactions, meaning they're pause for... Sorry, I had to pause. We had a bell issue. I didn't think you wanted to listen to that. So if the are slightly off balance, maybe you've drawn a Lewis dot structure and it's polar, but it doesn't involve hydrogen, fluorine, oxygen, or nitrogen. So if a polar molecule, it's going to still be dipole-dipole. This will require you to draw the Lewis dot structure. What if you draw a Lewis dot structure and it's completely non-polar? Then the only thing holding it together at all would be really weak, accidental, temporary forces, which are called London dispersion forces. These are very weak, they're temporary, and break very easily. Which leads us to number 29. So at number 29, we probably need to draw some Lewis dot structures. CH4, carbon, 2,4 hydrogens. This would be non-polar. You have extreme symmetry here, and there's no extra pair of electrons. So the only thing left would be these London dispersion forces. That would be pretty weak. And since those molecules would not be attracted to each other, they would break apart easily. What state of matter has particles broken apart and really far apart? Gases. This is very likely going to be a gas because it's so weakly connected to its partner CH4s on the planet. On the other side, we got this NaCl. You may remember a minute ago where I said molecules are made from just non-metals. Non-metals on the right side of the periodic table, since Mendeleev built it. Well, here we have a metal and a non-metal. This is a metal on the left side. This is a non-metal on the right side of the periodic table. This is an ionic compound. Remember ionic compounds, sodium's got a +1, chlorine's got a -1. They're attracted to each other because of their charges. This charge attraction is very strong. Very strong. This compound should have a very high boiling point because the extreme positives and negatives would be holding on to each other very, very tightly. Now we've got the other two. Alright. This thing is water. Water is one of these Fon situations. We have hydrogen attached to oxygen, so it's going to have strong hydrogen bonding. And then over here we have C with two H's and a Br and another Br. And any which way you build this thing, it's slightly polar. And if it's polar, it's going to have a dipole-dipole moment. And a minute ago, we put hydrogen bonding stronger than dipole-dipole and then stronger than London dispersion. So this one, while attracted to other molecules like it, would not be as strongly attracted as water molecules. So if I had to put these in order, I would say that this thing would probably be a solid because it's very strongly attracted to itself. You'd have to put a lot of energy into it to turn it into a liquid and even more energy into it to boil it, so it would have the highest boiling point. This thing at room temperature, most likely to be a liquid, and plenty of energy needed to boil it. This thing right below that one. And lastly, this one's probably a gas. You'd actually have to cool it off to liquefy it because its boiling point is so low. Number doesn't actually have a number. Let's call it number 30. Is there a 30? There is a 30. Number Q. All right. So for letter Q, we are supposed to identify each molecule as a molecule or ionic compound. If a molecule, draw Lewis dot structure. So first of all, molecules have what? Non-metals. Only non-metals. Ionic compounds have metals with non-metals. So you have to pull out your periodic table if you can't see it in your head. So this one's got a metal and a non-metal, so it's ionic. Metal, or so I've been told, iron is a metal, and oxygen's a non-metal. The other ones, well, they're molecules. So we'd have to draw their Lewis dot structures as instructed here. HF, that's a funny one to draw. CH2, it's got a double bond to the oxygen, 2 hydrogens. This one here, you got the carbon with the 4 chlorines. All right. I'm going to pause while I draw. All right. The drawings are all on there now. So let's just kind of go through. So this is number 1. This is HF. We've got hydrogen bonded to fluorine. Fluorine has 7 valence electrons. Hydrogen has 1. When they bond, they get to 8. Now that we've drawn this thing, we could see why it would be considered extremely off balance. You have fluorine with these extra 6 electrons on the right side, hydrogen's all by itself. Not only that, but this bond contains hydrogen's only electrons, so really you have a positive side over here and a negative side over there. It's almost like an ionic compound because you have a pretty strong positive and a pretty strong negative. Not a positive one, negative one like you have in an ionic compound, just a slight positive and a slight negative. Don't worry about those notations. But more to the point, this is one of the Fon elements. It's fluorine with hydrogen. It's definitely hydrogen bonding. This is number 3, formaldehyde. That smells good. Formaldehyde's definitely off balance. We've got 2 hydrogens on one side and the oxygen on the other. Does this hydrogen bond? Well, you've got the oxygen, you got the hydrogen, but is the hydrogen on the oxygen? No, it's not. The hydrogens are actually attached to the carbon. There is not another way to draw this. No. The 2 hydrogens have to be attached to the carbon and the oxygen is double bonded to the carbon. So it doesn't have hydrogen bonding, it just has dipole-dipole. Here is number 4. Number 4 has 4 chlorines. It's very symmetrical. It's the tetrahedral shape. It's definitely nonpolar. So it would only have London dispersion forces. Number 2 is right here. Number 2, phosphorus has 5 valence electrons. There's 2 sent up here on top that are by itself. It's that trigonal pyramid shape. Trigonal pyramid shapes are polar, so this would definitely have this dipole-dipole. Methanol. Methanol. Methanol is got this guy right here. Look at that. An O with an H on it. Unlike over here where we had the O by itself, no H, now we got the H. So, you know, that allows for hydrogen bonding in methanol. And then lastly, we have carbon dioxide, which is nonpolar, so it only has London dispersion forces, which is why it's a gas, because it's so weakly connected, it breaks apart pretty easily. All right. If you want to see cool YouTube videos of an interesting gas, look up carbon tetrachloride. It's a pretty cool looking gas. Very dense, awesome gas. And then lastly, before we end this video, we have the phase diagram 1. For each of the questions below refers to the phase diagram of mystery compound X. Actually, we kind of gonna bleed over. So this is really on the next page, but you can see the graph and see the questions at the same time here. So if you have a sample of this compound at 70 atmospheres, let's mark that down. And 200 degrees Celsius, 70 atmospheres, right here-ish. And you increase the temperature to 500 degrees Celsius, keeping the pressure the same. All right, we're going to cross through this line. We're going to go from the solid to the liquid. What do we call it when a solid turns into a liquid? We call it melting, right? If you say melting, I hear that's wrong. Melting. It's melting the solid as it goes from a solid to a liquid at that pressure and those temperatures. If you had a bottle containing compound X in your closet, what phase would it most likely be? Well, okay, what is the pressure? The pressure is 1, way down here. All right, what is the temperature? Right here. You're down here. The temperature, well, it's not 0. The temperature would be about here. Be somewhere in that range there. Most rooms are around 25. The pressure's down in that zone there. It's actually, technically, I guess we should be down here. Would be, you've gone by this scale, 0 atmospheres, a little bit above 0, so somewhere in here. Any which way you look at it, though, we are on this side. We are in the gas zone. So what have you got in your bottle? You've got gas. Number 32. At what temperature and pressure will all three phases coexist? So looks like it's about here. That is around 50. This is about halfway between 300 and 400. Let's call it 50 and 350. If you have a bottle of compound X at a pressure of 45 and a temperature of 100, 45 and 100, what will happen if the temperature is raised to 400? Right here. So you are going from solid to gas when you do this. You're going from the solid phase through to the gas phase. That is called sublimation. That is the term for changing a solid directly into a gas without melting it. Why can't compound X be boiled at 200 degrees Celsius? Compound X cannot be boiled at 200 degrees Celsius because at 200 degrees Celsius there is no liquid. In order for boiling is the conversion of a liquid into a gas. At 200 degrees Celsius, this substance is either a solid or a gas. So you'd have to raise the temperature pretty significantly and have a pretty weird pressure in order to get whatever mystery substance X is to boil. All right, we're going to end video 2 right